I think we all agree it is time for an example. And in this example, let A be our forward shift. But this time, because we want A to be invertible, not over the natural numbers, but instead over the integers. What does that mean? Well, A takes an infinite vector that is this time labeled over all integers, so it's a two-sided infinite vector. And just like before, everything is shifted by one position to the right. So in order to not lose our focus here, let's say that this is position 0, and on the other side, that is position 0, because otherwise it's hard to tell. So the spaces where these sequences are coming from could again be our LP spaces, but now obviously labeled over Z, the integers. Just to clarify this notation, let's say that for some index set I, which we usually assume to be infinite but countable, so you can count the elements, unlike the real axis or something like that, write LP of I for the set of all sequences of real or complex numbers, and the sequences are labeled over this index set I, with the usual LP condition. So you take all your data and modulus signs, then pth powers, then add up. Here you can see why we say that the index set I shall be countable, so we can write a summation sign, not an integral sign here. Okay, and then that result be finite. And if you want to go even further and introduce a norm here, then you would take the pth root of that expression and call that the p norm. In most cases, our index set will just be the set of natural numbers, 1, 2, 3, and so on. And because that is what we do most often, we introduce one more abbreviation. So the set LPN is just abbreviated by LP, which is what we've been doing for the last couple of lectures. Okay, that was just a little inset here to explain these notations. And now we all know what we're talking about. So let's look at our operator here. So it's taking such a two-sided infinite sequence and moving everything one position forward. Well, obviously this is an invertible operator, and the inverse is just the backward shift. Yeah, I think that doesn't need a long explanation. And recall that this would not be true if we had written the natural numbers here and here, and try to remember why. So in this case, we even know the inverse, and it's very simple. And nobody would really need approximation methods here to approximate the inverse or to approximately solve equations that include the forward shift, because solving them just involves the backward shift. But still, let's use this example as an example to play with and to try and understand what the finite section method is doing with this concrete example. Now, obviously here, having to deal with two-sided infinite sequences, we need our truncation operators to do truncations on two sides. Let's say they take your vector, and what they do is to delete all the data that is outside the interval from -n to n. And again, delete means replace by 0. Or we could just say it multiplies the original sequence by the vector that has 1s between position -n and n, and 0s everywhere else. Okay, now what happens if I use these operators Pn to produce my finite sections? Well, let's play column vectors here. I think that makes it easier to understand. So our two-sided infinite sequence or vector is first truncated by Pn. Then you apply the operator, which is the forward shift. So everything is moving down by one position here. Okay, and then you truncate again by Pn, let's say. And this will just erase everything that is outside these black lines, which are located at position -n and n. Okay, and that's your result. Now, if you want to study things like invertibility of Pn, Apn, then, like we said before, you cannot treat this as an operator on the whole sequence space. You have to restrict consideration to your subspaces Xn, which you take to be the image of your truncation operator Pn, which is just the set of all infinite vectors that look like this. And recall our notation where the star is just like a wildcard character. It's just standing for any free variable in these places, and all these stars are independent from each other. Okay, so what you do is you essentially focus on the vector that is between the two black lines, which is a finite vector of length 2n+1, I would say, and see what happens to that vector at the end. So it starts here and it ends here. And if you want to describe this action by a matrix, it would have to look like this. So like I said, we will restrict consideration to vectors in Xn, which are vectors looking like this. So we could say that instead of starting our journey here, we start here, where we are already in the image of Pn, because we have applied Pn. Okay, and then applying Pn, A, Pn, we end up here. Let's copy this quickly. And it's of course not too difficult to see what this matrix here has to be. Well, because of that 0 here, you have to start with the first row all zeros. Then in the next component of your result, you want a copy of the first component of your input vector. So you gotta put the 1 in the first position here, and the rest is all 0. And then that pattern continues until in the last row of your matrix you copy the, not the last, but the penultimate, the one before the last entry. So you have to put this one at that position. So you have once down the first sub-diagonal. That's what you say, that's what you call the diagonal that's just below the main diagonal. The main diagonal is full of zeros, and all the rest is zeros as well. And because of all these zeros above and below our black lines, it's clear that all the matrix entries surrounding this box here will be 0 as well. And like we said before, there is of course no chance for this infinite matrix here to be invertible because of all these zeros outside this center box that, by the way, goes from position -n to n, just like these here. But instead we look at this operator Pn, Apn as an operator that is restricted to the subspace Xn here. And of course its results are always in Xn. And in that sense here, all you're talking about is this finite square matrix here, which of course has a good chance to be invertible. If you look closely, then you see, well, this one is not invertible because it has a row full of zeros, or you could also say it has a column full of zeros. Or you could also say that you can already see it from the action of the operator, because it's filling zeros in where there was no 0, like this one's going from here to here. So you can see that the image is not using all positions anymore. The first one is by default always 0. And the other problem is that it's losing information, right? So this data which was at position n is simply lost. It's been deleted, and that of course means that you cannot recover the original vector from the output, which must mean you're not injective, right? So this means the operator is not surjective, and that xn getting lost here means it cannot be injective. And of course we know that property from linear algebra for finite square matrices. So this one is square, it's 2n plus 1 by 2n plus 1. And as soon as you break one of the two properties, surjectivity, injectivity, you also break the other one. Or in other words, if not every row has a pivot, then not every column has a pivot. Here you can see the pivots quite clearly. It's just the ones down here. And obviously the first row has no pivot, which corresponds to this loss of surjectivity here. And the last row has no pivot, which means this data in the last position is getting lost. So injectivity is lost. And obviously both these problems don't go away when you make n bigger. So if you make these finite sections bigger, then same two problems still occur. So no matter how large you choose your n, these approximations Pn, A, Pn here will always be singular, non-invertible. Which is of course something that we didn't see before. So when we had an invertible operator like our operator A here, the forward shift, and as long as we used uniform convergence approximation, then your approximants will sooner or later be invertible. Well, these ones are not. So this particular approximation method, which is of course nothing but the finite section method, is not stable and therefore not applicable